Hello. So we continue with the Laplace transforms from what Dr. Visaya taught you last week. So I just decided to start from the last example that she gave, where you now know how to find the Laplace transforms by evaluating the improper integrals. So this is the example, the last example she gave, the Laplace transform of t. Then you just go and substitute where there was f of t in the definition of the Laplace transform. And then you now solve the Laplace transform. I mean, you now solve the improper integral by introducing limits. And you then have to evaluate limits here and see to it that this one by L'Hopital's rule, another method that you can use will definitely give you a 0, and then this will be 1 over ace. So if you now put back the limits here and allow it to be infinity, then you have the integral from 0 to infinity of e to the power minus st, e to the power minus st dt, which was the Laplace transform of f of t is equals to 1. So that would be 1 over ace times the Laplace transform of 1, which is 1 over ace times 1 over ace, which is 1 over s squared, provided s is greater than 0. For this expression here to go to 0, then you need this condition. If this is not the case, then the whole integral will diverge. So this is what you did with Dr. Visaya. So there are different elementary functions that you can try, and one of them is the exponential function. And then I decided just to put the coefficient of t here as a constant r. So after you find the general solution, you can then replace a by any value that you want there. You can replace by 1, you can replace by -3, you can replace by 5, and everything will fall into place just so. This would be more of a general result for the exponent, for all the exponential functions of this form. So in the usual manner, the Laplace transform is basically going to be the integral where there was f of t, you replace it by e to the power at, and then this is the kernel of the Laplace transform that is always there. And then of course you use the laws of exponents here, and then you find that you now have s minus a as a coefficient of t with the minus sign at the outside there. And then you use now introduce the limits, and after that you do the integration. And when you do the integration, you then evaluate at the endpoints t and 0, and this is what you get. At evaluated t, you get this expression here. If you evaluate at t is equal to 0, then you get 1 over s minus a. Now, again, the same way, there are 3 conditions that you can use. So if s is equal to a, then you can see that this integral will not be defined. So it will not converge, it will diverge. So once it diverges, then it doesn't define a Laplace transform. And you can also see that once you put s minus a as negative here, then you will find that the limit of this expression, because once this is negative, then a negative and a negative will give you a positive number. So this will go to this expression here, the exponent here, will go to infinity. And once it goes to infinity, then we are in trouble, it diverges. Then, but if you take s minus a to be greater than 0, then you basically saying s should be greater than a. Then this is now positive, and this is a negative. So if the exponent goes to minus infinity as t approaches infinity, then e to the power minus s minus at will go to 0 in that case. So once this one goes to 0, then we know we have a finite value of the limit of these two. So this can only go to 0 provided s is greater than a. And the Laplace transform of e to the power at is 1 over s minus a, provided s is greater than 1. Now, this is important. If you leave this, then you are assuming you are just saying it works for all the three conditions, and that does not happen. We saw that the first two ones will not give us a convergent integral. So we need always to specify these conditions for convergence of the integral, so that we can have a Laplace transform in this case. So it is important to mention this condition for every function. Different functions have different conditions. So we need to mention it determines the existence of the Laplace transform of e to the power at in this case. So you can see the Laplace transform of e to the power at as just 1 minus the a that you have. So all it means, if a is negative, it is minus 1, for example, we just come here and replace a is minus 1, then we have 1 over s plus 1, and then here, provided that x is greater than minus 1. So if a is a positive number, like a is equals to 10 here, then it means you can just come here and then say, substitute a is equals to 10 there, then 1 over s minus 10, provided s is greater than 10. So that's how you find the Laplace transform of an exponential function e to the power at. Okay, so now we can try this on your own. What is the Laplace transform of e to the power 3t, e to the power minus 5t? Then do everything, the whole process here, with a is equals to 3 and a is equals to 5, and show that this is what you're going to get for a is equals to 3, and show that this is what you're going to get for a is equals to 5. And of course, the associated conditions need to be mentioned as well. And the associated conditions needs to be mentioned as well. So that's basically how we find the Laplace transform of the exponential functions.